This video establishes the essential mathematical framework for understanding vector and function spaces, focusing on the concepts of magnitude and standardization. It begins by defining the foundational principles of vector length within Euclidean spaces, which provides the intuition for a more generalized mathematical construct, the L2 norm. Subsequently, we will also detail the extension of this concept from finite dimensional vectors to infinite dimensional function spaces, thereby defining the criteria for L-squared spaces. It then introduces the critical procedure of normalization, exploring its theoretical motivations and practical applications. The exposition culminates in a computational demonstration that validates the theoretical principles we will discuss. The analysis commences with the foundational concept of vector magnitude in a familiar two-dimensional space. To formalize the notion of length, one typically invokes the Pythagoras theorem. For a vector v with components 3, 4, its length is computed as the square root of the sum of its squared components, yielding a magnitude of 5. This intuitive calculation of Euclidean distance serves as the basis for the more abstract concept of a norm. The L-square norm, also pronounced as the L2 norm, denoted by a double modulus on V subscript 2, is the formal mathematical generalization of this Euclidean distance. For a vector v in an n-dimensional space, the L2 norm is defined as the square root of the sum of its squared components. It provides a universal metric for quantifying the magnitude or size of a vector, irrespective of the vector's application, be it in physics, data science, or engineering. It is also known as the Euclidean norm. You can see that it is just the Pythagoras theorem generalized to any number of dimensions. So the L2 norm is like a universal ruler for vector spaces. It doesn't matter what the vector represents. The L2 norm tells you its magnitude or the size. To provide a concrete demonstration, we will now implement this calculation in Python. A vector v is equals 3, 4 is defined using the numpy library. The numpy.alignalg.norm function, which computes the L2 norm by default, is then applied. After running this code, we get the output of the L2 norm as 5, which confirms that the vector's length is 5. Now, this subsequent visualization plots this vector in a Cartesian plane, geometrically representing its components and its magnitude, which corresponds to the length of the hypotenuse. A significant conceptual extension is made when we consider a function as an infinite dimensional vector. Whereas a standard vector possesses a discrete set of components, a function possesses a continuum of values over its domain. To measure the length of such an object, the summation in the L2 norm definition is replaced by its continuous analog, the integral. The L2 norm of a function f of x is thus defined as the square root of the integral of its squared magnitude. The L2 space is thus defined as the set of all such functions for which this integral is finite. These are also known as the square integrable functions. Now that we also understood L2 spaces, let's move on to normalization. Normalization is the procedure by which a non-zero vector is scaled to possess a magnitude of precisely 1, thereby becoming a unit vector. The operation is straightforward. The vector is divided by its own L2 norm. The importance of this process stems for several key factors. The first one is standardization. It establishes a common scale for all vectors, removing the influence of magnitude to allow for the comparison of directionality alone. This is of critical importance in machine learning algorithms sensitive to future scaling. The next key factor is probabilistic interpretation. In domains such as quantum mechanics, the components of a state vector must adhere to the axioms of probability. Normalization ensures that the sum of the squares of these components equals 1, consistent with the total probability of 1. The last factor we'll look into is numerical stability. The process enhances the stability of various numerical algorithms by preventing computational issues like overflow. A useful geometric interpretation is the projection of any vector onto the surface of a unit sphere or in 2 dimensions, a unit circle. Now, we will now provide a computational implementation of vector normalization. The previously defined vector v is equals 3, 4 is used. First, its L2 norm is calculated. The original vector is then divided by this norm to produce the normalized vector. As verification step, the L2 norm of the resulting normalized vector is computed, which is expected to be equal to 1. So, if we run this is our output. The L2 norm of the original vector is 5, and the norm of the normalized vector is 1, which matches our theoretical base. So, this visualization effectively demonstrates this process. The original vector is plotted in blue, while the normalized vector is plotted in green. It is visually evident that both vectors share the same direction, but the normalized vector's terminus lies precisely on the unit circle, confirming its magnitude is 1. In summary, this video has detailed the progression from the intuitive concept of length to the formal definition of L2 norms and L2 spaces. The L2 space provides a framework for treating functions as vectors. The L2 norm serves as the metric for quantifying the magnitude of these objects. Normalization is the critical procedure for scaling these objects to a standard unit length, a requirement for fair comparison, probabilistic interpretation, and algorithmic stability. These concepts constitute a foundational element of the mathematical bedrock upon which much of the modern science, engineering, and data analysis is built.